This is our first section on integrals, and in this section we are going to learn a little bit about the notation and just basically what an integral is. Later on in this unit we're going to tie into derivatives. So derivatives may seem to be gone initially, but they're going to come back at us. What we're going to talk about today is what's called a definite integral. And if I could pick one word to mean integral, the word association I want you to think of is area. So when I say integral, you think area. Just like when we said derivative means slope, slope means derivative, that word connection, that word association with an integral is this word area. So our integral represents the area, which is A, you have a little picture here, between the graph of f of x and the x-axis on an interval, in this case from A to B, and you see that represented in this graphic right here. This is what the notation looks like. This is an integral sign. It looks like an elongated S, and at either end there are numbers that represent an interval. The lower limit is A, your upper limit is B, and that just represents an interval that goes from A to B. This part right here is the integrand. That tells you what function you're dealing with. Sometimes if you're given a graph, it's just generically called f of x, but sometimes you might actually be given an expression here that we'll see when we get to our examples. This dx part tends to cause people confusion. They want to make something of it, but just think of it as bookends of that integrand. So an integrand is always going to start with that integral symbol, and it's going to end with a dx. That x is just the variable that's represented in this f of x. So if you had a function whose independent variable was t, out here you would see a dt. And this is read, and I have it in quotes down here, the integral from a to b of f of x dx. So we begin at the bottom, so we read it from the bottom to the top. So the integral from a to b of f of x dx. So it's reading from bottom up, not from top to bottom. And again, those limits are just giving you your interval so that you're finding the area of a finite region. Let's go ahead and take a look at a few examples. So our directions say to evaluate each integral by graphing and using area formulas. Over here on the left side, I've got some popular area formulas that we're going to use on these problems. As we go through this unit, you're going to learn different techniques for evaluating these. And even though it's based on area, you're going to find that it's not always about graphing and finding the area. That's just what we're starting with because it's very intuitive and it hits at the heart of what an integral is, and that is area. So if I need to find the area of a region, I first have to find what that region is. So question number 1 says to evaluate the integral from 1 to 3 of 2x plus 1 dx. My first job is going to be to graph y equals 2x plus 1. It is a linear equation. My y-intercept is at 1 and my slope is 2. So I go up 2 over 1. And next I look at my limits of integration, which gives me my interval. So my interval is going from 1 to 3. I'm going to block this off from x equals 1 to x equals 3. The region I'm interested in is bounded by that graph of f of x, the intervals, and the x-axis. Always use the x-axis, never the y-axis. So here's my region in here. I recognize this as a trapezoid. These red sides are my bases. My height is the distance between those bases, which is a 2. To find the length of each of these bases here, instead of trusting your graph and reading from the graph, take that x value and plug it into the function to get your y value. What I get is my y value here is a 3. So this first base is 3 units long. And if I plug a 3 into my y equals equation, I get a 7. So the length of base number 2 is a 7. And now I'm ready to use my area formula for a trapezoid. So it's 1/2 times the height, which is 2, times the sum of the bases, which is a 3 plus 7. And I get my final answer here is a 10. So the value of that integral is simply 10. On example 2, you may or may not recognize this expression, but what I have to graph first is y equals the square root of 9 minus x squared. I'm going to transform this a little bit, and it might turn into something that you recognize. So I'm going to clear that square root by squaring both sides first. and then move the x squared over. And that is the equation of a circle centered at 0, 0 with a radius of 3. Don't get too hung up on it if you don't remember how to do that. It's not a big, huge part. Since this was only the positive square root, I'm only going to draw the top half of that circle. And applying the definition of the integral, I need to be bounded by the graph of f of x between -3 and 3 and the x-axis. So my region is this semicircle here. So I'm going to find the area of a circle and divide it by 2. Since the area of that semicircle is 9 pi over 2, the value of my integral is 9 pi over 2. You can represent that in a variety of ways. There's nothing wrong with writing 9 pi over 2. If you wanted to write that as 4.5 pi, that would be fine. If you wanted to put that in a calculator and turn it into a decimal, it would be 14.137. If you decide to go the decimal route, just make sure you give me 3 decimal places at the end. Carrying your answer out to 3 decimal places is a rule that applies throughout the AP exam. So whenever you give me a decimal, make sure it is 3 places accurate. Let's go ahead and take a look at another one. On the back side, we're evaluating the integral from -3 to 4 of 2 dx. What's important about this is my integrand is simply a constant. So I'm simply graphing y equals 2. And then I take a look at my limits. I'm going to bound this from x equals -4 to x equals 3. So from -4 to 3. I'm going to pay attention to the region that's bounded by y equals 2, my limits of -4 and 3, and the x-axis. And my region is this rectangle. The base of this rectangle is 7, and its height is 2. So the area, which is also the answer to my integral, is just 14. This question leads us to a little bit of a shortcut down here. Whenever you have the integral of a constant, when you go to graph that, it's going to turn out to be just a horizontal line. And when you put your limits on there, it will always be a rectangle. So it's always going to be finding the area of a rectangle. Just a shortcut to find those dimensions. And you see it happening in that example that we did in number 3. The base of your rectangle is just the difference of the limits. So up here, I could have just done the 3 minus -4 in order to arrive at that 7. And then the height is just whatever that function value is, which in this case was a 2. So whenever you have the integral of a constant, you can use this little shortcut. If you forget, you can always graph it out and look at that rectangle and find its dimensions and its area that way. If this video has put you to sleep, it's time to wake up because this next part is really, really, really important. It's what we call signed area. And so far we've talked about an integral as being area. However, there's one thing you have to remember. If you have any area that falls below the x-axis, we're going to take that area as a negative. And that kind of defies what you think area should be because all your life you've been told area is positive, 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 and it's true. But when it's taken in the context of an integral, any area that falls below the x-axis gets taken as a negative. One quick example will show you how this works. I'm asked to evaluate the integral from -3 to 3 of f of x dx. Notice it doesn't give me an equation here, it just refers me to this graph of f of x. I'm going to take a look at my limits that go from -3 to 3, and I'm going to block it off from -3 to 3. It just kind of forms a natural barrier at the 3. And I'm going to find the area that's trapped between the graph and the x-axis. Between -3 and 1, that area is above the x-axis. But once I move past -1, when that graph of f of x dips below the x-axis, my region is now below the x-axis. I'm still defining that region as being the area that's trapped between f of x and the x-axis, but this time it's below the x-axis. I'm interested in the areas of these two triangles. So this red one, the area is 1/2 times the base times the height. The base is 2, and the height of it is also 2. Finding the area of the yellow triangle, its base is a 4, its height is a 2, so the area is going to be 4. Since the red triangle is above the x-axis, I count that as a positive area. But since this yellow triangle is below the x-axis, I take this 4 as a negative. So when I go to evaluate the integral, I'm going to take a positive 2, I'm going to add a negative 4, and I get a final answer of negative 2. And it seems to not make sense when we say an integral is area, and all of a sudden here I'm getting a negative answer. But the way that you interpret that negative is it just means that I have more area that lies below the x-axis than I have lying above the x-axis. As we move through this integrals unit, we're going to learn some really cool applications of this. We're going to tie it to derivatives. But for right now, all you really need to know is it's all about the area.